Okay, continuing with the study guide, I stopped on number 13 with the videos. And this is one that I did in most of my classes today, so you may have already got notes on this, but that's okay. So this one is about the electroscope. This is a device that detects a charge, whether it's present. Like it doesn't measure it. It just, if there's a charged object outside of the electroscope, then the foil leaves. These are like aluminum foil and the ones I made. If they have the same charge, they're going to repel from each other and move apart. So you can tell kind of what's happening with an outside charge in terms of what the leaves are doing. So what we want to do is match these electroscopes to what's happening with them. Okay. So some clue words that we're going to look for. A negative rod is brought near the top of a neutral electroscope. Brought near means induction. That's our no-touch method of charging. And whenever we have induction, our objects end up the opposite charge of each other. Okay. So let's say a negative rod is brought near the top of this neutral electroscope. And the answer to this one is B. So I'm just going to go ahead and draw. Here's a negative rod. When this is brought near the electroscope, the negatives in the top of the electroscope are going to go down into the leaves. They don't want to be near this because like repels. That's going to leave less electrons in the top. So that makes my top positively charged. My leaves are negatively charged and they repel because they're like charges. Okay. So I've got like an opposite charge here. None of these charges are transferring between this rod and the electroscope. This is just making charges move around in the electroscope. Okay. Likewise, just skipping down a bit, if a positive rod is brought near the top, so again, induction, in this case, we're going to have a positive object brought near our electroscope. That's going to make our negatives want to come up near it because they're attracted to it, they like it, and that's going to leave less negatives in the leaves, making them positively charged and making them repel. Okay. Touches, that is conduction. Remember, that requires contact, and my objects are going to end up with the same charge. So if I touch a negative rod to my electroscope, let's say this is D, so I'm actually going to touch the top of the electroscope with this rod. These excess electrons are going to go down into my electroscope. Okay, so that's going to make my electroscope negatively charged as well. And then if I've got a positively charged rod that I touch it with, that means this is lost electrons somehow. So some electrons from the electroscope are going to go into this object. We still are going to have a lack of electrons between these two, okay? Because now this one already had a lack of electrons, and now some of my electrons from here are going to go into here. So I end up with two positively charged objects. The last electroscope is grounded by a copper wire. So I drew this little grounding symbol here. That means we have a way to get rid of excess electrons. And so if we have a charge build up on our electroscope and then we have a grounding wire attached, all those electrons that are extra can go out through the grounding wire and my electroscope goes back to being neutral. And I know that because my little leaves are hanging down, not repelled from each other. Okay. Okay. Number 14. All right, so this next couple of problems have to do back to the electrostatic force. So I wrote my equation here. Constant times one charge times another charge divided by the distance between them squared. Okay. So this one's got some numbers in it, but we can still do this almost like a factor of change if we look at what's happening. We've got a 2 coulomb charge and a 3 coulomb charge, and they repel each other with 20 newtons of force. Okay. So the first thing we want to know is what would be the repulsive force between a 2 coulomb and a 6 coulomb charge at the same distance. So this is having to do with these charges, but now we're saying one of these is going to double. Instead of 3 coulombs, it's going to be 6 coulombs. If I double one charge, if charge goes up, then my force goes up. So if I double a charge, that means my force value is going to double. Nothing else is changing. So doubling a charge, right, doubles the force. So that's going to give me 40 newtons. It was 20, now it's 40. Okay, this one, I'm assuming it's the same two charges, okay? Now we're saying that we want to know what the force between a 6 coulomb and a 6 coulomb would be if the distance was doubled. So here we got several things happening, which is a little confusing, but our first charge is tripled because it was 2 and now it's 6. Our second charge is doubled because it was 3 and now it's 6. And our distance is doubled. Okay. So if I want to get what that factor is that's going to change my force value, then I've got 3 times 2 divided by 2 squared for my distance. That's going to give me 6 over 4, or that's 1/2, I think, if I'm remembering correctly. 6 divided by 4. Yep. So now my force is 1.5 times larger than it was. Because these two charges have gone up. My distance was doubled, but both the charges increased. One tripled and one doubled. So I'm going to end up, instead of 20 newtons of force, I'm going to have 30 newtons of force because I'm going to have 1.5 times more. Okay. So these are kind of like factor of change, and then in the end, we're just applying them to a number that they actually gave us. How much would the electric force between two charges change if they move from 1 centimeter to 4 centimeters apart? So my distance here is quadrupling. Okay, it's going from 1 to 4. So I would say my force is, I'm going to say 1 times 1 because my charges, nothing happened with those. Okay, we're just looking at distance. My distance went up by 4 times. I have to square that. So my factor here is going to be 1/16. My force is going to drop by 1/16 if my distance quadruples. Here they move from 4 centimeters to 2 centimeters apart. So here my distance is dropping in half. Okay. It was 4, now it's 2. So again, force 1 times 1, because I'm not changing the charges, divided by 1/2 squared gives me 1 divided by 1/4. And when I flip this, I multiply by the reciprocal, I end up with 4 times. So when I bring my charges closer together, my force is going to go up by 4 times the amount if I drop that distance in half. Okay. There's going to be one more video after this one.